Hello, Calculus 3 students. Hope everybody had a nice spring break. My spring break is unfortunately still going because flights were canceled. So, in lieu of having class on Monday, which would be March 23rd, I made a little video just to conclude material going into the second major exam, which, again, as a reminder, our second major exam is going to be on Thursday, March 26th. Okay. I believe we did have a homework that was due on Monday, so I'm going to push that back until Wednesday. And I also wanted to give you another homework going into this second major exam. So I will post that on our Canvas page, and that will be due on Wednesday, March 25th. Okay. But we don't have much left to cover going into the second major exam, which is nice because we already started talking about equations of tangent planes when we were looking at functions that were implicitly defined. This just wraps things up with functions that are explicitly defined. And it's a very short and sweet lesson, so I don't plan to spend a ton of time on this, but it's just looking at the formula again. It's a little bit different than what we've seen before, but basically it's just a special case of the formula that we derived the Thursday before spring break. So that's my plan. Exam is still scheduled for Thursday, and I hope that I'll be back on Wednesday. So I have a flight tomorrow, so hopefully that flight will be on time and it won't be canceled. So, but anyway, hope everybody had a good spring break. Okay, so tangent planes for functions that are explicitly defined. You got z equal to f of xy. Okay, so this, again, as I said, this is just a special case of what we did before when we were looking at the function f of xy z equals 0. If you remember that part. Basically, what you need to do is you need to substitute in this equation into the correct form. So you can rewrite this f of xyz to simply be a difference. You got a z minus f of xy, and you can set that equal to 0. So again, this is basically, again, just substituting in this formula, but taking the difference of these things, and you'll still have a function in terms of x, y, and z. Okay. We're looking at a specific point. In this case, because I think the way the textbook does it, they use AB and then they use f of AB. If you want to convert this to a C value, you can certainly do that. I've seen some books do that. Let's take the gradient evaluated at this point. So we're going to take the gradient of this capital F and see what we end up with. So basically, we need to resort back to this form with this difference, and we take the gradient of each piece evaluated at the point. So if we start by taking the partial with respect to x, notice here we got a negative in front of this f of x, y, z. So the first part of the gradient is going to be negative f sub x evaluated at whatever this point is. So I'll just put in terms of a and b because, again, this is just a function of two variables in this case, comma, partial respect to y. Notice again you still have a negative in front. So this will be negative f sub y evaluated at ab. There's that part. And then you want to take the partial of this thing with respect to z. Well, if you take the partial of this thing with respect to z, you get something very, very nice. You get back 1. So hopefully that makes sense to you. Again, we're evaluating at this point of interest at AB and then f of AB, but again, we're only taking into consideration a and b because we have a function of two variables for this portion. But again, when we take the first partial derivatives, we got a negative in front. So what does this tell us? So if we proceed, as we did before, an equation of the tangent plane to the surface where z is explicitly defined to be in terms of x's and y's at this point of interest AB. Here are your coefficients in front of your differences. So this one, and this one. These portions that are in red come from the components of the gradient, which you've seen before. Notice we have minuses and minuses here. Here we got a positive, okay? Notice this part here, this is z minus z sub 0, but the z sub 0 in this case is going to be this portion of the point thrown into the mix. So you see that there? If you rearrange terms a little bit, so in other words, you distribute out this partial, negative over this partial, negative over this, distribute out the 1 over this. Not going to change this at all, but what you can do is you can solve this thing out for z. Basically, this will be negative, negative. You'll have a negative here. You can get those terms over to the other side, and you can solve this thing out for z. So that's the formula that we're going to have for an equation of a tangent plane for z equal to f of xy. So I wrote it here, but I'll read it to you. You let f be differentiable at the point of interest, so AB, whatever it is. An equation of the plane tangent to the surface when it's explicitly defined at the point of AB, and f of AB is simply going to be this. That's the formula that you need. Again, this formula is, of course, in standard form. We could put it into general form by doing out the distribution of all the constants and simplifying stuff so we don't have fractions like we did before. But this is going to be our formula that we're going to use. So hopefully that makes sense. And we can do a little example. All right? Okay. And again, this derivation is the exact same derivation that I had, but it was typeset nicely on the PowerPoint. When we come back to class on Wednesday, okay, I'm going to give you a couple more problems to look at. I'll give you like a little worksheet just to make sure that you understand what was going on in this video lecture, because again, I'm not there, unfortunately, but I'll give you some more problems when we come back to class on Wednesday. And then Wednesday, we'll spend going over stuff for the second major exam. Okay, let's do an example. All right. Let's find an equation of the plane that's tangent to the paraboloid. All right, so of course we know what that looks like. That's your bowl shape. Okay, it's given by all this stuff, and it's at this point of 2, 1, and 16. All right, so we need the formula. So how about if I just copy down the formula? So we got z equal to f sub x evaluated at 2, 1, times x minus 2 plus f sub y evaluated at 2, 1 times y minus 1. And then we need plus f of 2, 1, but we know what this is. That's 16. Right? Because remember, this is the xy coordinates, and that's the corresponding output for the z. So this 16 will eventually be substituted in for this value. Okay, let's start with figuring out what the first partials will be. So I'll do that here on the side. So f sub x of xy. Partial respect to x looks like it's going to be negative 6x. And while we're here, how about we do the evaluation at the point? So I'll have f sub x evaluated at 2, 1. So it looks like that's going to be negative 12. Okay. F sub y of xy. So we need the partial, excuse me, with respect to a y in this case. So it looks like that's going to be negative 8y. Evaluate this at the point of 2, 1. So it looks like that's going to be a negative 8. Okay. Hopefully that evaluation makes sense to everybody. Let's start substituting things in. So we're going to get z equal to, this portion is negative 12. Negative 12 into x minus 2. This portion here is negative 8 into y minus 1. And then this portion here, as I said before, that's going to be your 16. So there's the answer. In standard form, we can, of course, simplify this a little bit and put it into the general form. So I'll show you both ways. Okay? So distribute, 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 distribute. I get z equal to negative 12x plus 24 minus 8y plus 8 plus your 16. Okay. So we're going to have z equal to negative 12x minus your 8y. And then, of course, we need to just simplify out to figure out what the constants are going to be. So we got this 24, we got this 8, we got this 16. So 24 plus the 8 plus the 16, doing it mentally in my head. I believe that's 48. So there it is, right? 24, 8, and 16. Yep, 48. There it is. So if you want to, I suppose you could leave the 48 on this side and get these two terms with variables on the other side. So you could have 12x plus 8y plus z equal to 48. That would be your answer in the general form. So either one of these answers will be totally acceptable. If the exam was asking for one specific form versus the other, then, of course, you give the appropriate one. But hopefully that makes sense. Okay. The last little topic that's in this lesson that concludes material for second major exam is what's known as normal lines. But we've seen normal lines before. Because remember, normal lines, if you have some sort of a surface, let's just say that this is our surface down here, and you have some sort of a point of interest on this surface, if you want to get a normal line out of this, so the line that goes like this, so the pen going straight up to the document camera, of course, you can get two vectors. You can take the cross product between them, and you'll get a vector that's normal. In other words, orthogonal to both. We know how to do this already because we've seen before that our gradient vector will give us the normal vector, because that's how we derived a lot of these topics already for the tangent plane. So, knowing that information, let's take a look at this problem. Let's find a set of symmetric equations for the normal line at the point. So we got negative 2, 1, negative 3 to the ellipsoid, which is all this stuff. Now, of course, ellipsoid, not a function, but that's okay. We can still figure out for this ellipsoid, and I'll try to draw something. All right, so there's your ellipsoid, whatever it is. Here is a point of interest on this ellipsoid, okay, so negative 2, 1, negative 3, whatever it is, and you want to find the equation of the line in symmetric form that's normal to that point. Okay, so what do we need? You got to figure out what the gradient is first, okay? And then we can take the gradient, evaluate it at this point of interest. That will give us our direction numbers to form out our symmetric equations. And then hopefully you guys remember how to do out the symmetric equations, but the symmetric equations look something like this, where you have x minus x sub 0 over a equal to y minus y sub 0 over b equal to z minus z sub 0 over c, where the a, b, and the c, remember those were our direction numbers. Now our direction numbers are going to come from our gradient. Okay. First things first, it is an ellipsoid, so it's not a function, but it is defined implicitly. So if you want to, you can rewrite capital F of x, y, z to be this x squared over 4 plus y squared plus z squared over 9 minus 3 equal to 0. You can bring the 3 over to the other side and equate everything out to 0. The constant here of negative 3 and the 0 are not going to contribute to the gradient, but you can write f of x, y, z to be this. So I just wanted to point that out to you. Okay, let's find the gradient. Okay, so we're going to need first partials. So partial respect to x, bring down the 2, leave x by itself, reduces by 1. So 2 over 4 gives us a half x. This one's going to give us 2y. And this one's going to give us 2z over 9. There's our gradient. Let's evaluate this gradient at this point, negative 2, 1, negative 3. Let's see what we get. Okay, so it looks like we're going to have a half times negative 2, comma 2 times a 1, comma 2 times negative 3 over 9. So this is going to be negative 1 for this one. This one's going to be a 2. This is going to be negative 6 over 9, which that can be reduced by 3 to be negative 2/3. So these give us the A, B, and the C, our direction numbers that we would need for these values. So our symmetric equations for this normal line will simply be x minus, so it's x minus x sub 0, so we need the x sub 0 point. So just as a recall, this is x sub 0, y sub 0, z sub 0. So this is going to be, looks like it's going to be plus 2 over negative 1 equal to y minus 2. I'm sorry, y minus 1 rather. Sorry, y minus 1 over 2 equal to z plus 3 over negative 2/3. So that would be our symmetric form for the normal line. And again, on the PowerPoint, I have a nice, beautiful picture of this. I did not do this justice, but I do have a nice picture of this on the PowerPoint, so you guys can look at that. But I would not ask you to graph that. I would only ask for this portion. So hopefully that makes sense. That concludes all material for second major exam for this Thursday. All right. The practice exams, solutions, and the homework that was supposed to be due Monday are outside of my office door. They're in an envelope, so if you haven't gotten those, please go up to my office in COAS 301.03 to pick those things up. Yeah, this concludes all the material, so hopefully this all makes sense. Okay, what I would also like to do, because I was planning on doing this on Monday, is I would like to give you just a little bit of a preview for material going into the third major exam. So let me give you a little preview of things to come. This is what's known as absolute and relative extrema. You've seen absolute and relative extrema before in Calculus 1, but now we can do absolute and relative extrema with functions of several variables. So let's say you have some sort of a surface. Say it's this surface here. So this is going to be your z equal to f of x, y. Of course, passes through. It passes the vertical line test. You take a vertical line parallel to the z-axis. It's only going to go through it once. You're good to go. All right? And let's say that you have some sort of a domain. And again, I did not draw this well, but I have nicer pictures on a PowerPoint for you, which I can post. But let's say that your domain is this. So in other words, this is your projection, your shadow that you would get if you were to stand here. You got a light source. You project the light source onto this blue surface. This is your projection onto the XY plane. Okay. We can talk about absolute versus relative extrema. Remember, absolute extrema means it's the highest point that a function takes on for a certain interval in Calculus 1, but now it's going to be on a set D. And relative means if you're on an open set, what is the highest point and lowest point that a function takes on. So just looking at this, maybe this point right here could be an absolute minimum. I mean, it looks like a low point. I don't know what it is. We probably will need to find that at some point. And maybe this point that's way up here, maybe this could be an absolute maximum point. It's the highest point that the function takes on. This, of course, with the absolute maximum, absolute minimums, this is, of course, true because we're bounding this surface, whatever this is, onto a domain. If this was, let's say, dotted all the way around, then this could be maybe a local minimum and this could be a local maximum because maybe the function dips down here and maybe it finally goes up again. Who knows? It depends upon what the behavior is of the function and it depends upon which point we're looking at. If you're bounding it though, hopefully you guys remember this, we have extreme value theorem. So if we're bounding this with extreme value theorem, which we are with this purple region, there is at least one point in R at which f takes on a minimum point. All right, so could be that one, but we'll have to test it. And same thing, there's going to be at least one point in this region. Oh, I called this D. I should really call this R just to make it consistent with what I had there. There's going to be at least one point of f that takes on a maximum point. There could be more, there could be ties. Ties really happen if you have trig functions because, again, they're sinusoidal curves, but there are other cases as well. I have an example of that. But you can use this extreme value theorem to figure out, okay, if we're on a closed bounded set, which we are here, we're guaranteed to have at least one absolute max, at least one absolute minimum. Guaranteed to have at least one. These things could happen at a boundary point. So boundary point meaning if this is our true absolute minimum based on this picture, the corresponding point, if you were to map this thing back to the XY plane, is right on the boundary. It's on the edge. That's how I always like to think about it, of this domain, this region R. Whereas this absolute max, this happens at an interior point that's on this region here for the domain. You have this interior point versus the boundary point. These points here, these are called critical points. And we can find critical points just like we found critical numbers of functions of single variable. So critical points, it's basically the exact same definition, what you had back in Calculus 1. You let f be defined on an open region R containing whatever the point is, x naught, y naught. X naught, y naught is going to be a critical point of your function of several variables if one of the following is true. Your first partials both equal to 0 at the point, or the second case, one of these partials, or both, because there's an or in here, does not exist. If you remember back in Calculus 1, it's the exact same thing, but it's involving just a regular old derivative. So it's either going to be the derivative is going to be set equal to 0, or the derivative is not going to exist. Same sort of thing is happening here, but we have to take into consideration partials because, of course, we have multivariables. Hopefully that makes sense. So what we're going to be doing is we're going to be finding critical points, both interior versus the boundary. And again, if we have boundaries like this, then we're going to have absolute extrema. Absolute extrema, that will involve a little bit more of a process, so I'm not going to do that here today. But I can at least help you get started with finding critical points, because that's going to be important. Because if we can't find the critical points, then we can't figure out where we have the extrema. So let's do an example of a critical point. Okay. So I have one little example here. And again, I'm just going to give you a little introduction. I'm just going to go through the process on how you can find critical points of this, and I'll end the lesson. So let's find the critical points of this function. So you got f of xy is equal to xy into x minus 2 times y plus 3. Okay. What's nice about this is already factored. But it's not factored really in the correct stage that we need in order to get the constructive information that we need to find critical points. Because we got to find first partials. All right. So what I would do, I would multiply everything out and get the resulting polynomial function that represents this, not in the factored form. All right, so we got xy into, all right, these two together give you xy, these two plus 3x, these two minus 2y, and these two minus 6. Okay. Let me distribute. So we're going to get x squared y squared plus 3x squared y minus 2x y squared minus 6x y. Hopefully that makes sense. Now let's start the process of figuring out where we're going to get critical points. And before we do that, let's address this question. This is a polynomial of two variables. So since we have a polynomial of two variables, is it differentiable everywhere? Is it continuous everywhere? Yes. Yes, it is. It is both differentiable and it's continuous. So in terms of critical points, the ones that we need to look at, the only ones we need to look at, are these. Number one. Those are the ones that we need to look at. This case is out because, again, we have differentiability everywhere. We have continuity everywhere. We have a polynomial of multivariable. So we need to take our first partials and set them both equal to 0 and see what we get. And then along the way, we're going to factor. Okay, so in no particular order, I'll do f sub x of xy first. Okay, see what we get. So we need first partials. Okay, so this is going to be 2xy squared plus 6xy minus 2y squared minus 6y. Hopefully that partial differentiation makes sense to everybody. Let's set this equal to 0, and let's see what we get. We'll try to factor this. Okay, well, what I'm thinking is maybe we try to factor it by grouping, because we have 4 terms here, and we can't combine stuff. So let's see. Common out of these first two, it looks like we can pull out a 2xy. So we're going to be left with, I think, a y plus a 3. Hopefully that makes sense to everybody. And out of these two terms, I can take out a negative, and I can also take out a 2 and a y. So I'll take out a negative 2y, and I'm going to be left with y plus 3, and this is all set equal to 0. Well, this is very, very nice because, again, with grouping, this term and this term are the same, so I can pull out the common factor of y plus 3. So I'll get y plus 3 into 2xy minus 2y equal to 0. I can factor a little bit more. I can take out a common y between these two terms, and also I can even take out a common 2. So maybe I'll write it this way. 2y into y plus 3 into, looks like it's going to be x minus 1 equals 0. So hopefully that makes sense with the factoring. Now out of this, if I use the zero factor property, if I set this 2y equal to 0, I'm going to get y equals 0. If I set y plus 3 equal to 0, get y equals negative 3. And if I set x minus 1 equals 0, I'll get x equal to 1. Does that make sense? Okay. Hope it does. Okay. Hope it does. Let's take a look at what happens with f sub y of xy. Let's see what we get. Okay, so now we take partial with respect to y for this. Okay, so it looks like it's going to be 2x squared y plus, looks like it's going to be 3x squared minus 4xy minus 6x. That's just taking the partial of this with respect to y. Set it equal to 0. All right. Again, I'm going to try to factor by grouping. So between these two terms, it looks like I have an x squared that's common. So I'll have 2y left over plus a 3. And out of these two terms, I have a common negative, I have a common 2, and I have a common x. So I'll take out a negative 2x, and I'll be left with 2y plus a 3. And this, again, is nice because this and this are the same things, so they're common factors. I can take those out. So I'm going to be left with 2y plus 3 into x squared minus 2x equal to 0. And I can take out a common x squared out of these two. So maybe I'll write it this way. We got x into 2y minus 3 into x minus 2 equal to 0. Okay? Okay. And of course, I'm going to get roots out of this. I mean, I'll get x equals 0. I'll get, let's see, what would I get here? This would be y equal to 3/2, and this would be x equal to 2. So that's what I would get. Now what I need to do is I need to take, because again, basically what we have here is we do have a system of equations here, but they're in terms of partial derivatives. What I need to do is I need to take each one of these values, substitute them back in for these, and crank out what the points are going to be. You could also do it this way. You could also take the roots out of these, which would be x equals 0, 2, what did I say before? Y equal to 3/2. You could take these, substitute them back into these, and crank out what the points are. It doesn't really matter how you do it, but since I did these ones first, I'll just put them back in for here and see what we get. Okay, so in no particular order, maybe I'll start off with y equals 0. Okay, so if I put in y equals 0 into this first partial, I'm going to get, let's see, I'm going to get x into 0 minus 3, x minus 2 equals 0. So it looks like this is going to be negative 3x into x minus 2 equal to 0. Zero factor property tells me this guy is going to be x equals 0, and this one is going to be x equals 2. I have 2 critical points so far. I have, so critical points, I have 0, 0, and I have 2, 0. So I have 2 so far. Let's do y equals negative 3 and see what we get. So I'll take y equals negative 3, substitute in for this. So I'll have x into 2 times negative 3 minus 3 times x minus 2 equals 0. So I'll get x into negative 6 minus 3 into x minus 2 equal to 0. It looks like this is going to be negative 9x into x minus 2 equals 0. So same deal. This will give me x equals 0. This will give me x equals negative 2. I'm sorry, x equals positive 2 rather. So positive 2. So I actually get a repeat. I do get a repeat, because this will give me 0, 0, and, oh no, I'm sorry. I'm not going to get a repeat because I'm doing it for y equals negative 3. So I'm going to get critical points being 0, negative 3, and I'm also going to get 2, negative 3. I was looking at the 0 here, and I should have been looking at this one because this is the one I'm doing. All right, so I get 0, negative 3, and 2, negative 3. Okay, so far I have 4 critical points. Let's see what happens when I do x equals 1. All right, so I got another sheet of paper here. So x equals 1. Okay, so I'm going to put x equals 1 into, I'll just write this out here again because I ran out of room in the previous page. Okay, so I'll put in x equals 1 in for this and see what we get. So it's going to be a 1 into 2y minus 3 times 1 minus 2 equals 0. So 1 minus 2 is negative 1, so this is going to be really negative into 2y minus 3 equals 0. That negative 1 is not going to contribute much to anything, but we're going to get solutions out of this. This will be y equal to 3/2. So we get a critical point here being 1, 3/2. So let's summarize everything. Critical points. So we got this one, 1 comma 3/2. We have, from the previous page, we have 0, 0. We got 2, 0. We got 0, -3. And we got 2, -3. We have 5 critical points. Very interesting. So now what we need to figure out is, what are these points? Are they relative maximums, minimums, or maybe something else? We'll have to see. And we're going to have to see how this thing works using what's known as the second partials test. If you remember back in Calculus 1, there were 2 tests that you guys used to look at extrema values. And the 2 tests were the first derivative test and the second derivative test. Okay? Well, we don't use these tests anymore in Calculus 3. We use what's known as the second partials test. But that's going to be later. I think this is a good place to stop. Again, you can look at you can look up what the second partials test is, because that's what we're going to be using. But we will continue this after the second major exam on Thursday. Okay, so again, I apologize for missing for missing class. For this Monday, but hopefully I can get back into town soon. But again, thank you very much for listening, and I will see you all very, very soon. Bye.